Picture this. You're standing right there on the bridge of the massive GF-12,000 drillship. It's totally quiet at first, but then the navigation console lights up piece by piece, and the whole room just comes alive. You've got the digital gyro compass spinning up to speed, radar sweeps doing their rhythmic rotation across the screens, electronic charts glowing in the dim light, and this one small, steady icon pulsing in the corner, letting you know the Voyage data recorder is capturing every single second of it. Today, we're diving into the incredibly intricate world of marine electric navigation, specifically looking at how a state-of-the-art drill ship finds its way without ever, and I mean ever, resorting to guesswork.
So let's start with a really fundamental question. How exactly does a massive vessel, and we're talking about a ship displacing 77,000 metric tons, which is basically the weight of over 200 fully loaded jumbo jets, how does it manage to navigate safely without ever guessing its position or heading? Because long before the ship's massive dynamic positioning thrusters can even engage to hold it steady over a wellhead, the computers and the bridge team need to know exactly where the ship is, which way the bow is pointing, what obstacles are around it, and how fast it's moving. And the absolute golden rule here, they have to do all of this without relying on a single point of failure. No exceptions.
And the answer to how they pull that off lies in something called the principle of intentional disagreement. On a highly advanced drill ship like the GF-12,000, you don't just have one instrument telling you where you are. Instead, you have a full electronic navigation suite that acts kind of like a jury of witnesses. These independent instruments are constantly measuring, and more importantly, they are continuously cross-checking each other. If one sensor starts to drift or fail, the others essentially just vote it out. The whole entire system is built from the ground up on the idea that no single instrument should ever be trusted blindly.
Let's jump right into Section 1, the core, finding the true heading. Right, so before you can possibly know where you're going, you obviously have to know which way your bow is pointing. To find that true heading, vessels contrast two entirely different physical principles side by side. On one hand, you have the traditional transmitting magnetic compass, and on the other, you've got the modern digital gyro compass. Now, the magnetic compass relies on a physical needle that literally aligns with the Earth's magnetic field. Meanwhile, the digital gyro compass relies on a rapidly spinning mass that seeks true north by using the Earth's rotation. So they're measuring the exact same thing, the ship's heading, but they are using completely, fundamentally different physical principles to do it.
And here is the really crucial point. Having both of these systems isn't just some redundant overkill. It is a very deliberate design choice, specifically so that they fail in entirely different ways. Think about it. A magnetic compass can be thrown off by nearby ferrous metal or some unexpected electrical interference. A gyro compass? Completely immune to that. But it is vulnerable to mechanical breakdowns or total power faults. By combining two vastly different technologies, you essentially guarantee that a single environmental hazard or system fault won't knock out both of your heading references at the exact same time.
Which brings us to a massively critical operational rule of thumb for the bridge team, the heading cross-check principle. Basically, if you see a persistent disagreement between your magnetic compass and your gyro compass, you must investigate before trusting either of them. I mean, it's just human nature, right? Especially on a high-tech drill ship, we automatically want to assume the highly advanced, incredibly expensive digital gyro compass is right, and the old-school magnetic compass is wrong. But doing that completely violates the whole purpose of having them both. A discrepancy means there is a puzzle to solve, not a default winner to choose. You might even need to cross-check with a third reference, like GPS course over ground, just to figure out exactly which instrument is actually lying to you.
Moving right along to Section 2, the surroundings, seeing through the storm. Okay, so moving outward from the ship's internal heading, the vessel actually has to detect its immediate surroundings, which is especially important when visibility drops to zero. To pull this off, the GF-12,000 uses a really fascinating mix of radars, split between X-band and S-band frequencies. Now, X-band radar gives you incredibly high detail at a short range, making it absolutely perfect for delicate jobs like docking or close-quarters maneuvering with supply boats. But because of its high frequency, it performs pretty poorly in heavy rain or sea clutter. S-band, on the other hand, operates at a lower frequency. It gives you a lower detail picture, sure, but it can cut right through heavy weather and sea clutter at much longer ranges. So understanding which radar to prioritize isn't just some trivia fact. It is a vital, practical skill for the bridge team when a clear day suddenly turns into a blinding squall.
And, to make sense of all those hundreds of radar blips, the ship relies on ARPA, or the Automatic Radar Plotting Aid. This system works seamlessly with both the X-band and S-band radars. Instead of a human operator having to sit there and manually calculate where another ship is going based on past radar sweeps, ARPA automatically tracks the course and speed of nearby vessel contacts. It instantly slaps a predictive vector right onto the display, showing the bridge team immediately if another ship happens to be on a collision course. It's an absolute game changer. Next up is Section 3, the environment, depth, speed, and charts. To track its physical progress across the globe, the ship relies on some really rapid-fire environmental sensors. First up, you have the echo sounder, which is constantly pinging the seabed to measure the exact water depth beneath the hull. Then there's the dual-axis electromagnetic speed log. This thing doesn't just measure your forward speed. It actually tracks the vessel's speed through the water on 2 different axes, which is incredibly crucial for a vessel that frequently moves sideways while maneuvering on dynamic positioning. And finally, we have ECDI, the Electronic Chart Display and Information System. This has completely replaced those giant, unwieldy paper charts of the past, integrating the ship's real-time position directly onto dynamic, highly detailed digital maps.
Let's move into our final area, Section 4, the record, the ultimate black box.
So, we've seen exactly how the ship knows it's heading, how it spots traffic, and how it maps its environment. The final layer of this whole navigation suite is the system that is quietly capturing every single bit of this data. It's called the VDR, or Voyage Data Recorder. It functions exactly like an aircraft's black box. It is continuously and silently logging everything: the radar images, the heading, the speeds, the radio communications, and even the ambient audio on the bridge. Honestly, nobody really thinks about the VDR during a routine sunny transit, but its entire value is realized in that rare, awful event that something actually goes wrong. It provides an objective, unbiased record of exactly what the instrument showed and what was said, ensuring that any incident investigation relies on hard, undeniable facts rather than stressed-out human memory. But this brings up a genuinely crucial operational warning from our sources. VDR data integrity must never be assumed. A VDR that is simply powered on with its little lights glowing is completely useless to you if it hasn't actually been saving the data to the drive. Regular verification is absolutely essential, because think about it, you only ever find out you need the VDR after an incident has already happened, and by then, it's way too late to fix the recording gap retroactively.
And that brings us to a final thought for you to chew on. Technology provides this massive continuous stream of data. We've got gyros, radars, depth sounders, and automated plotters doing incredible math in real time. But who investigates when these incredible instruments actually disagree with each other? The answer is always the human operators. The automation on a modern drill ship is absolutely staggering, but it is not infallible. The ultimate safety of a 77,000-ton vessel relies on the bridge team vigilantly cross-checking this chorus of instruments, noticing the subtle little disagreements, and thinking critically before a tiny data glitch snowballs into a massive physical disaster. The technology doesn't replace the mariner. It just gives them better tools to navigate the unknown.